Okay, so today we are going to consider the following system of linear differential equation. This system has states x1 and x2, and the system has parameters a and b. Okay, so the motivation for this exercise is because we want to understand how to pass in parameters into the ODE solver. The reason why this is important is because when we start designing controllers for our dynamical systems, okay, we need to understand how to pass in the control signals into the ODE solver. Okay, so we need to pass in the control signals so that our dynamical system can follow a reference trajectory. Okay, also in an adaptive control, in an adaptive control design, we also need to pass in the unknown parameters of the system into the solver so that our adaptation mechanism can estimate the unknown parameters. Okay, so, and another thing I want to point out from this exercise is how to define the ODE function in a more optimized fashion. Okay, and to do that, I'm going to have to write this system as a matrix equation. Okay, so to write this system as a matrix equation, you will note that I can rewrite this system as this right here, okay? Because this can be converted back to this. Okay, all I need to do is to perform the matrix multiplication, and then you'll find out that this is equivalent to this, okay? So having defined the system as a matrix equation, I can simply make the following definition, okay? So I define x1 and x2 transpose as the column vector x. Okay, so, and also the matrix, this 2 by 2 matrix, I store this 2 by 2 matrix in the variable or in the parameter a. Okay, so with this definition, I can therefore write this system of linear differential equation as this matrix linear differential equation. Okay, so without wasting any time, let's go into the Google Colab environment to define or to implement our system. Okay, now the first thing I'm going to do right now is to import the ODE solver, which is available in the SciPy library. So I'm going to say from scipy.integrate import solve IVP. Okay, solve IVP is a function, is the ODE solver in the Python environment. Also, because I need to plot my results, I'm going to import the matplotlib, okay, .pyplot, okay, as PLT. Okay. Now the next thing I want to do is to define the ODE function. Okay, so I say ODE fun, and I'm going to use a placeholder for the time variable. Now, the reason I'm using a placeholder for the time variable instead of defining time explicitly is because the system is an autonomous system. Okay, so you can see that the system doesn't depend on time explicitly. Okay, the variables x1 and x2 are dependent on time directly. But if you look at the right-hand side of the system, we do not have time written explicitly. Okay, so the system therefore is an autonomous system. So since time is not included in the system definition, I'm using a placeholder for the time slot. Okay, because the system is an autonomous system. Then our vector x, I have it right there. Then the parameter a, and then the other parameter b. Okay. Now my matrix a, I can define it as this. Say a 1 1, and then 1 b. Okay. So I have just defined my matrix, and then the ODE system, the x, the t equals a matrix multiplication with the vector x. Okay, then I return the x, the t. Okay, so this is my system definition. Now the next thing I want to do is to solve the system. So I can now use the function solve IVP, which I imported in the first line. Okay, so solve IVP is the ODE solver. So what I want to do now is to pass the function, the ODE fun. Okay, now I want to integrate this system from 0 to 8, from 0 to 8. Okay, and my initial condition, the initial condition of the system as given in the system definition is 0.1 and negative 0.5. Okay, so now I have a 0.1 and negative 0.55. Okay, now to pass in my parameters, I'm going to use the optional the parameters args. Okay, then I'm going to pass in the parameters -1 for a and -1 for b. Okay, so this is all there is to this solution. Okay, I am required to plot my results. So I'm going to say plt.plot s.t. Okay, let me first of all output x so that you see why we are assessing the data that way. So if I click the run button right here, okay, so I have an error in the system. Okay, no module, matplotlib. Okay, so I have matplots. I missed the T there, so I just included the T. Matplotlib. Okay, so I hit the run button again. Okay, here we go. Now I'm interested in these fields, T and Y. Okay, so this thing is being held in the variable S. So to access T, I'm going to say S.T. Okay, and to access Y, I'm going to say S.Y. S.Y, for example, S.T right here. Okay, so here is my T, the T data. Okay, now the S data, S.Y gives me the Y data. Okay, so you can see that the Y has two rows. Here is the first row, and here is the second row. Okay, to access the first row, I'm going to say S.Y of 0, and to access the second row, S.Y of 1. Okay, so now to plot the result, I'm going to say plt.plot. Okay, because the plot function is in the matplotlib library. Okay, and I've stored it as plt. I've imported it as plt. So I'm going to say plt.plot s.t, comma s.y, the first row, s.t plotted against s.y, the second row. Okay, so I hit the run button again. So here is my solution. And keep in mind, the purpose of this is to understand how to pass in the parameters. So that is a key takeaway there, right? So another thing I want to point out quickly is that, as you can see, this solution is not so fine. If you want to make the solution more accurate, then you can reduce the relative tolerance error. Okay, by default, the relative tolerance error is 10 to the negative 3. So I can make it smaller. Say, for example, relative tol equals 10 to the negative 6. Okay, then I run the simulation again. So here I have it. You can see this solution looks much finer than the previous one. Okay, so the key takeaway here is passing in the parameters for the system definition into the ODE solver. Okay, that is the key takeaway. Thank you for being part of this exercise. Okay, so I will encourage you to subscribe as more videos are coming. Like, share, and subscribe. Okay, thank you.